structures. You're to read this data in, right? And each of these rows here corresponds to a structure. So you have to declare a structure data type. And your job is to create a structure called employee, which contains the fields down here, or identified up above, but these are examples. Use a dynamic array of pointers to structures to hold the data. Instead of having to pass all the parallel arrays to the various functions, you can simply pass your array of pointers to structures. So you're going to have to do a new, right, for each one of these structures, each one of the structures. And this one, I'm going to let you do your choice, I guess, whether or not the array for John and the array for Smith are dynamic or not. You can have these as static, fixed length, just because it makes it a little easier this time. That won't always be true, because with structures, certainly the structure itself could be dynamically allocated, and each of these elements, the first name, the last name, social security number, pay rate, number of hours, and something as simple as whether it's full-time or part-time, the letter designation could also be allocated dynamically, each and every one of those. So what you would have is an array of structures, or you'd have a dynamic array of structures, but each of those structures contains nothing but pointers. Okay? We'll get there. This time we'll make it a little easier for you. Questions on what it is you're to do for this week? No? Okay. I wanted to go back, look at chapter 13. We introduced it a little bit before. We've talked about structures. I want to introduce this notion of a type def statement. I think we've mentioned it. In C, type defs far more important than they are in C++, or you see them much more commonly used. I like type defs. I like to be able to call something like a char splat and give it a name called pchar. Okay? There's a tendency perhaps to forget what that actually is, but nevertheless we can type def them and assign a name. What do you suppose ushort is? Unsigned short, a data type. So we would use a type def command to define the name ushort as a type name. Understand ushort, ulong, pchar are not variables. And that's where we get into a little trouble. They look like variables. They're not names I'm familiar with. They're names I made up, and therefore have tendency to look at them and say, oh, that's a variable. Not so. And so the custom, not a requirement, certainly, but a custom is to make these type def names all uppercase, so that it helps us to identify a type def versus a variable name. So the way we do it is keyword type def, the data type, however complex it might be, followed by the type def name and a semicolon. So from that point on, I can use pchar to be my char star. Well, it's no difference in terms of characters, number of characters for typing, but we might want to use that instead of char star. Okay. Enumerated data types. They're useful in C++. There was a time in some other languages, in particular Pascal, in which enumerated data types were throughout the language and used extensively and supported extensively. In C, they're just kind of a wrapper around some other stuff. So their value is, in my opinion, somewhat limited. You may find them the greatest thing since sliced bread, and I encourage you to use them. Enumerated data types are useful as a documentation tool. There's nothing introduced here that hasn't already been introduced. Just another layer, if you look at it as an onion or something, just one more layer added on to mask all the nitty-gritties of 1, 2, 3, 4, 5. Okay? Enumerated data types. Associate lists of identifiers with the type name. And variable of this new enumerated type has the value specified in the identifier list. Syntax is enum. And some people pronounce that enum, which is probably more correct than the way I say it. I always say, and I can't break the habit, enum. Okay? An enumerated data type, so we are defining this type name to be an enumerated data type, followed by the list of values that belong to that. An enumerated data type is like saying, well, I only want a variable that can take on the even numbers. So if you give me an odd number, it's not part of that type. It doesn't belong to that type. And there involves another value of having enumerated data types. The compiler can check to see if the value that you are assigning or working with matches and fits the enumerated data type. It has value in that regard.
So can you put logic in that then? For the identifier list?
Yes, you could say true and false in here. That's the way we did it back in C days. We would do a Boolean, create our own Boolean type, and have just two values. Here's a couple of examples. Button state, off, on. Now, in some other languages, like Pascal most notably, the word off and the word on were actually objects. They were actually things that you could print out. You say print out button state sub whatever, and it would print out the word off, or it would print out the word on. In C, when we go to print, C out it, whatever, we peel the layer back and we get a 0 or a 1. So its usefulness in that regard is somewhat limited within a C and C++ environment. But button state is a type that can take on only these two values. Anything outside of that range, the data type does not support it. You'll get some kind of a declaration error or assignment error or whatever if you try to set it to something else. Clear? What's the value, Dwight, what's the value in the type traffic light color for yellow?
1.
1. How did you know that?
Because it starts at 0 in increments.
Because the list, by default, starts with 0. Red is 0, yellow is 1, green is 2. Now, being a graphics person, I could certainly map red to be some collection of bits, right? I can assign it that way. And I can assign yellow to another collection of 32 bits. Perhaps useful if I am trying to constrain and check, do some type checking with respect to colors. What day of the week is Sunday? 0. Okay? And this is not an issue of religion. Okay? It's an issue of enumeration. Sunday is 0. Now, if you move Sunday and you moved it down to there, what would Sunday be?
6.
6. Okay? Is that clear? We can restart and specify different enum associations. So here, ACE, instead of being defaulted to 0, turns out that we set it to 1. So what do you suppose deuce is? 2, and tray is 3. Okay, all right? Over here, we can enumerate all of them. Penny is a 1, nickel is 5, dime's 10, quarter 25. We can specify each and every one of them if we would like, or take them by resetting the starting point or the midpoint value, whatever it might be. Then, when we have this data type, this is a data type, isn't it? Days of the week is a data type. Today is the variable. Now we get into, again, we have to be able to recognize when we look at code, where's the variable name? What is its data type? Because now these things start to look the same, don't they? Just by looking at them, because all of them are identifiers. But what are we identifying? Here, the highlighted piece is a data type. It's actually an enumerated type that we had back here. So today can only take on values Sunday through Saturday. Can only assign it one of those values. Anything else is out of range. We can create arrays of these things, right? And initialize a week to be Sunday through Saturday, all right? We can do dynamic allocation of those things. And we can do straight assignments. Saturday, that one looks like, oh, it should be the R value of Saturday is assigned into best day, right? Well, in essence, it turns out that it is, right? Because what's going to actually be assigned underneath the hood, peel back the layer of the onion, what's going to be assigned into best day? 6. Okay, we're assigning Saturday, and that's a real nice documentation feature, isn't it? Just say Saturday. Okay. Printing an enum. Here's where the layer of the onion gets ripped back. And I don't know why C++ didn't follow this through to its logical conclusion, because if it did, then it would be much more useful. Here we have cout best day. We know best day is Saturday. That's the object, Saturday. But cout says, to heck with you. I'm going back to native mode. I'm printing out a 6. All right? Is that clear? I'm sure somebody somewhere along the line has figured out how to overload cout. You could probably do that as an exercise in 136. To overload cout so that it will print out Saturday instead of 6, recognizing the data type. If we want to actually print out the word Saturday, we have to resort to something that's very obvious, I think. We create an array of strings and put our values in there, and then use this index, best day, to print out the string, to see out this string. Everybody understand this line of code right here? Okay. Enumerated data types. Here's an example. Menu choice. We have menu items defined or declared to be add is a 1, so delete is 2, edit is 3, exit is 4. We ask somebody to type in or respond to our menu choice, enter a menu choice, and then if menu choice is in range, we can do this, which is a nice documentation feature, isn't it? But the user, in response to this prompt, does not type in the word add, delete, edit, or exit. They have to type in a number. And so the enum piece kind of falls short. Once they've entered in the number, that's cool. Now we can do a static cast. Notice the requirement that we have to cast menu choice, which is integer, to a menu item's data type, and then we can use it for add, delete, and so on. Okay? And that's the rest of the menu manipulation thing. Structures, we've looked at this already, so this I hope is going to be a little bit of a review for you. Structure, a structure and a class are identical in C++. Anything you can do with a class, you can do with a structure. Anything you can do with a structure, you can do with a class. The only difference is structures are public by default and classes are private by default. Syntax, the word struct, it's a key word. And then the struct name, you make it up, it's an identifier. And then data members inside of the parens or the curly braces. Notice that this is our declaration for a student struct. And so let me ask you, how much memory does this allocate? Dakota? What I've got highlighted, how much memory does it allocate? The answer is 0. This is only a declaration of a type. Okay? The type name, just like with enums, the type name is student here. So now we can say student something, but it is a type. No memory is allocated for this highlighted piece at all. It's only a cookie cutter, if you will. It's only a template of what will come when we actually do the allocation. Is that clear? So having declared the student data type to be a structure with an integer which is 4 bytes